So I would like to switch to our next topic and start talking about unsupervised learning and generative models, and we'll continue this discussion next. Actually, there is no lecture next week, so the week afterwards. So let's remind ourselves. So we talked about many architectures. We've seen different variants of CNNs. We've seen multi-layered perceptrons. We've seen RNNs, but the training regime that we discussed so far was common for all these models. So I remind you that we had some finite sample, essentially from this space X cross Y. Okay, X, what we called it an instance space, and Y we called it a label space. And we wanted to find a model that was approximating our target function, which I called F. Okay, the function that given an instance produces a label. And of course you can think of it in the probabilistic setting if you prefer, but the idea is the same, right? So we wanted to create such a hypothesis that approximated the labeling function. So we wanted to infer how this function should transform X to Y based on some finite samples from pairs of X's and Y's. Okay? And we solved this problem. We assigned some loss function for individual points. We took the average of these loss functions over the entire training set. We call this the in-sample loss or the empirical loss. And hopefully I convinced you that if we are smart enough, then minimizing this empirical loss can actually do something that generalizes well. So basically it will also produce low values of the expected loss, which is something that we care about. Okay, and what I would like to ask you now is, suppose we don't have access to labels. Okay, can this unlabeled training set still be useful? So we have many instances of our data, but we don't have labels. For example, we have collections of images. Let's say we have a zillion of images from Google, but we don't have any class labels. Why is this? Why is this so? For example, because labeling costs money. And we don't have money to pay for labeling. So we have many data points, we have many instances, but no labels. Can we still do something useful with it? Okay? And I would like to remind you one very powerful principle. Well, it's not a scientific principle. You can argue to death whether this is philosophically meaningful, or not, but at least it is a useful heuristic. Okay, so it is usually attributed to Wilhelm of Occam, an English Franciscan friar, and basically I think he never wrote it. Actually, it is attributed to him. One of the typical statements of what he presumably wrote was something like "Ense non sunt multiplicanda praeter necessitatem," which means that you shouldn't make the number of entities more than necessary. And in our language, it will say that we would like to keep minimum the number of degrees of freedom for two hypotheses that describe the same scenario. So if you have some data which are described equally well by two hypotheses, then keep the one that has the smallest number of degrees of freedom. And again, there is nothing scientifically founded underlying this principle, but it is a good heuristic. It keeps you parsimonious. It keeps you basically as cheap as possible, if you will. And if we look, for example, at how real data look like, it appears this is again an empirical observation that works well in many cases, that while we have real world data that are embedded in a very high dimensional space, for example, just take an image, a very modestly sized image, 256 by 256 pixels, will reside in our 65, let's say 65K dimensions, right? 65,536, right? This is a huge dimensionality, right? But if you just take a random point, let's say with uniform distribution in that space, with overwhelming probability, you are not going to get anything that looks like a natural image, right? It will be just noise. So you can then augment this statement by saying that real world data actually come from some space with a low intrinsic dimensionality. Okay, so you can put different rigorous definitions behind this statement. What it means by having low intrinsic dimensionality. For example, one of the ways of making this statement rigorous is by saying that the data lie on some low dimensional manifold. Okay, or they come from a probability measure that is supported on a low dimensional manifold, if you prefer a probabilistic setting. Or you can have different mathematical tools, like for example the Gaussian mean width, that are proxies to dimension. Okay, so essentially it means, for example, if my images come from a two-dimensional manifold, it means that I just need 2 coordinates to describe them, right? Instead of 65,000 coordinates. And of course it means that I have less degrees of freedom to generate such points. So I will define a new training regime, which we're calling unsupervised learning. In unsupervised learning, we don't have a label space. We have just the instance space, just the data, but it might still be very meaningful to discover the structure of the data. For example, we have this cube of images. How exactly they are distributed inside? So I have examples of natural images. They form some low-dimensional space there. I would like to discover it without caring of which image is a cat and which image is a dog. Okay, so it is still a meaningful task to discover the structure of the data. And then I might go one step further and I can say, actually, I want something synthetic, something that a black box, I hit a button and it spits out a natural image. So I would like something that generates samples from that distribution, something that can generate data obeying that structure that I discovered. Okay, and these are called generative models. So basically, the two ideas are very related to each other. Unsupervised learning means that I would like to discover the structure of my data, and one of the ways of discovering the structure of my data is actually building a model that can synthesize new data. Okay, and basically, this is what we are going to deal with. So let's do a very simple exercise. I'm sure the result will be completely unsurprising. So let's assume that we have some hugely dimensional data space, and here huge means 3 in my drawing. And let's say we have a 2-dimensional data subspace, or in general some k-dimensional data subspace, k significantly smaller than n. So in this case, let's assume that our data subspace is a linear space. Okay. So it's just this plane. So if I want to be rigorous, linear means that the origin is included in this space. It can be a general affine subspace if you want to be more general. Okay, but let's keep it linear for simplicity. So linear means that, for example, points lying on this plane are my data points, and a point lying outside is not a data point. Okay, and basically I'm now given a bunch of training samples, and I would like to approximate them by this plane. Okay, so let's do this mathematically. I have my training data. Suppose I have big N training sample. So each sample is a vector. It's a small n dimensional vector. Okay, and suppose this small n is still big. Let's say 65,000 is in our example of images, and I would like to impose a linear subspace model. Let's say I would like it to be of dimension k, much smaller than n. Okay, otherwise I'm not reducing the number of degrees of freedom. So I'm taking my input data points and I would like to represent them in the following way. So I would like to represent them as a product in some subspace basis. So these are vectors of the basis, can be any basis, let's say an orthonormal basis, if you will. Its dimension k, it means that I just have k such vectors. These are, of course, column vectors of dimension n, right? And I multiply them by a vector of coordinates. Okay, so a coordinate for every, so basically a vector of k coordinates. These are short vectors, just k dimensions for every data point. And of course I have n data points, so there will be n such columns. Okay? Say it again? No, unrelated to Word. Well, Word2Vec can be produced using this kind of analysis, though it can be also created using different tools. But basically what I did now, I factorized my matrix X, of course, only approximately factorized, into two factors. One of them is a tall matrix with k columns. Another one is a short matrix with k rows, right? And of course here it has dimension small n, and here it has dimension big N. Okay, so I factorized my matrix into two factors. Okay, what is the rank of this matrix? Of this factorized representation, what is the rank? Maximum rank is k, right? So I started with the matrix that potentially had full rank. So let's say rank n. Suppose n capital is bigger than n. So I have zillions of examples. Okay, and I now approximate this matrix by a rank k matrix, which I can always write in this outer product form. So then my unsupervised learning problem can be stated as find the closest approximation to my original data matrix in this factorized form. So give me the two factors that approximate my matrix, let's say in the L2 sense. Okay, this is a completely rigorous statement of a problem, right? So this is what I mean by discovering the structure of the data. Give me this basis, give me the corresponding coordinates. Now, of course, can it be a generative model? Of course. I will just randomize a new set of coordinates, and I will still stay in that data subspace, right? So I can spit out new points. Okay. So now when you see, so essentially I'm looking for an L2 optimal rank k approximation of X. When you hear about some reduced rank approximation optimal in the L2 sense, you immediately think about what numerical technique? Well, PCA is another name. You think about SVD, right? Singular value decomposition. So singular value decomposition for every matrix tells us that it can be factorized into the product of two orthonormal matrices U and V transpose with the diagonal matrix sigma here that contains non-negative values that are called the singular values of the matrix. And of course, for a square matrix, it can be easily related to eigendecomposition, right? Now, if I take only the coordinates corresponding to the largest singular values, usually singular values are ordered in the decreasing order, I will have an L2 optimal k rank approximation. So here I just took the first k columns and the first largest singular values, k largest singular values, and of course k rows of vk transpose. Okay, so just call this W and call this A. And this is exactly our L2 optimal k rank approximation of X. Okay, so in general, this is a non-convex problem because we have a product of two matrices that are optimization variables, but this is one of the few non-convex problems that have a closed form solution. Okay, and this method in statistics is called principal component analysis. So you have essentially a linear model, and it can be made in a fine model as well. You can put some offset vector here as well. It is called principal component analysis. Basically, the columns of this factor W are called principal components. And you can create new data points by just, again, taking, for example, random coordinate vectors and multiplying, basically taking the linear combinations of the principal components with those weights. I guess I didn't tell you anything new, right? This is how PCA is built. Now, in practice, the linear assumption can be very restrictive. Real data might reside on something like that. So this is some kind of a non-Euclidean manifold. It doesn't obey a global linear model. We can still work with some local linear models. This is what, for example, Gaussian mixture models try doing. But in general, we would like to discover this nonlinear structure in the data. Okay, and PCA is very restrictive. We can do kernel PCA, but kernel PCA, the nonlinear part of it is not learned. So you need to transform with some fixed kernels into some fixed kernel space, and then do regular PCA. And our answer to these approaches is by saying no, we are going to work directly with nonlinear maps, directly with nonlinear models. And our way to embody a nonlinear model is, of course, by using neural networks. Okay. So basically, the setting of discovering the data structure is generally termed dimensionality reduction, right? So in PCA, we reduced the dimensionality from n to k, and it was linear dimensionality reduction. Here we want to do nonlinear dimensionality reduction. So suppose we start with our instance space x, we take our point x, and we map it by a map that I will be calling an encoder from the original instance space to some new representation space z, okay, which let's assume will be k-dimensional, as in our previous example. And here, let's say the original instance space is n-dimensional, again as in our previous example. So I'm going to map my point from the instance space to this representation space, and this map is going to be called an encoder, and then I'm going to map it back to synthesize new point. So I take the representation vector and I map it back to the instance space. Okay? So PCA did exactly this by projecting my data on the basis U, on the factor W that I call. I'm creating a vector of coordinates, of k-dimensional coordinates, which reside here in this latent representation space. I'm discovering this space. And then when I multiply this vector of coordinates by W, I create new n-dimensional vectors which map me back to the instance space. And of course, there will be some discrepancy here, right? Because it's only an approximation. So now I can formulate my unsupervised learning problem as an attempt to minimize this discrepancy. So ideally, I would like this map to be an identity map. I would like the encoder to take me to some representation, then the decoder to take me back exactly to the same point where I started. So that would be an identity map. Because you see, the composition of phi with psi is a map from x to x. And I would like it to be the identity map. So in the case of PCA, what prevented me from being an identity map? No. Well, everything is linear. So why didn't I get the original data points? Why was it an approximation? Exactly, because I restricted the dimension of this representation space to be much smaller than n. Okay, so I introduced some sort of a bottleneck in my representation. I fixed the number of dimensions in the representation space. So unless my data are really perfectly representable by a k-dimensional parameterization space, I'm going to lose information. Okay, so it is up to me now to select the two maps phi and psi in such a way that I'm going to lose the least amount of information with respect to some discrepancy measure. And of course, it's a very big question how to select this discrepancy. Well, one of the ways will be to learn it together with the two maps, and this is one of the interpretations that we are going to give to generative adversarial networks, to GANs. Okay? But let's say we fix some distance here, let's say the L2 norm for simplicity. So then I can train for a pair of maps, and of course we want complicated, rich, nonlinear maps. I'm going to embody them as two neural networks. Let's call them phi and psi with parameters alpha and beta. Okay, so I'm going to minimize the discrepancy over the training set. So essentially, I don't have supervision. My data are my supervision. So I would like to map the training point x by first phi, then psi, and I would like the result to be similar to x. Okay, and I would like this to happen for every point in the training set. So I'm minimizing this loss. This is an unsupervised loss. There are no labels mentioned in any place in these terms. And graphically, I can think of it this way. I take some high dimensional input x, so this is a very high dimension. This is dimension n. I'm squeezing it through a bottleneck of dimension k, okay, and some information is lost. And then I'm expanding it back to an n-dimensional vector. And I would like the input and the output to be approximately the same in the sense of this discrepancy d. Okay? Of course, if I don't put any restriction on this bottleneck, I can generate identity transformations if my models are rich enough, but that's not the point. I would like the bottleneck to be small. And of course, there are many interesting theoretical questions. How do you automatically discover the dimensionality of your data? But you can do trial and error. You can try different sizes of the bottleneck and see how well you can recover your data back from this representation. Okay, and this model is called an autoencoder. So we are encoding and decoding the data in such a way that preserves the maximum possible amount of information within the restriction of the bottleneck. Okay. So one of the popular architectures for an autoencoder is a convolutional autoencoder. So as you can see in this picture, this until here, this is an encoder. And from here on, this is a decoder. And let's implement both as CNNs. So in a CNN, so at least our abstraction of a CNN is a network that takes an infinitely dimensional, d-dimensional sequence signal and produces another d-dimensional signal. So basically, we are independent of the size of the input. But we can still do we can still do strided convolutions or pooling, right? So the lattice in the input and the lattice of the output can change. So we can produce output on a less dense grid. And by producing an output on a less dense grid, we can essentially reduce the number of dimensions in the output. Though the number of dimensions both in the input and the output is infinite, but every sample in the output corresponds to many samples in the input. Okay, so basically, by doing a sequence of such decimations, we are reducing the dimension of the input. Okay, so then a technical question that arises. So suppose I'm creating an architecture here that does this squeezing, that does this decimation. How do I do the opposite direction? Okay, so usually we think of a CNN something that reduces dimension, right? How do I do the opposite operation? And though it is not necessary, but it would be nice actually to think of this as a mirror. So basically, if I went here from dimension, let's say n to dimension m, I would like to go here from dimension m to dimension n. Oh, just because of the beauty of being symmetric, right? Just because of the aesthetics. Yes. No. Again, we don't have infinitely dimensional inputs in general. So suppose you have an image, let's say 256 by 256 pixels, right? And let's say you have a few layers, and every layer decimates the image by a factor of 2 in each direction. So after the first layer, you have 128 by 128, then 64 by 64, then 32 by 32, then 16 by 16, then 8 by 8, and let's say you stop with 4 by 4. So this is 4 by 4. This is 256 by 256. Okay, so obviously you reduce the dimension, right? Now you would like to go backwards. So we know that a CNN reduces dimension, but let's see how we do the opposite operation.
So how can the image of that 4 by 4 give me more than 16 different results?
Why 16? It's a 16-dimensional space, but it is a continuum, right? Well, in practice, the input image is quantized, but the number of quantized images that you can have of this size is bigger than the number of particles in the universe, right? Even with 8-bit quantization. It's some humongous number with, I don't know, with 10 to the power of, I don't know, 10,000, something like that. Okay? So basically, I would like to answer this technical question: how we do these expanding decoder convolutional layers. Okay, so let's have a look at some math. So we have a regular convolutional layer that we have in the encoder. It accepts an input of dimension m. So basically, it has m feature maps. It's a d-dimensional signal. Let's say d equals 2. It's an image. Then we do strided convolution. Strided convolution with some downsampling factor p, and then we produce another infinite sequence, again with an index of dimension d and n feature maps. But basically, you see, we decimated the density of our lattice. So if we instead of taking this infinite index, we take something of finite support, then the support was actually reduced by a factor p in every dimension. So the number of pixels was shrunk by a factor of p to the power d. Okay, so obviously this does dimensionality reduction. It decreases the dimensionality, and the convolution, of course, is given by this expression. We saw it already, right? And then I have this decimation, which is what strided convolution does, right? Strided convolution is p acting on j. So I'm throwing everything except, so I'm retaining only the pth sample of the output. Okay, and so basically I'm applying this decimation to the output. Again, this is different from dilated convolution. In dilated convolution, we, instead of doing subsampling, we did upsampling of the kernel and not of the output sequence. Okay. So again, we start with an input x, want to produce an output y. We do convolution and then add some bias and apply nonlinearity. This is what our single convolutional layer in the encoder did. It does a nonlinear transformation and reduces dimensionality. Now let's see how the decoder should look like. So obviously we want a map from y to x. And we know that this map was not invertible. We reduce dimension. So if it were linear, it wouldn't be a square matrix. And plus we have some nonlinearity, right? So obviously there is no inverse to this map. But if you think of a linear transformation, you have a matrix A of size, let's say, n by m. Okay, so we have a matrix of size n by m. It maps from Rm to Rn, right? It is not invertible, but which matrix would map back from Rn to Rm? Well, but I don't want to mess up with inverses. I don't want to share the same parameters anyway. I just want some general recipe, something that will give me the same dimensions. Transpose, right? If I write A transpose here, it will give me the, at least in terms of the range and the domain and codomain of this map, will give me the desired dimensions. Of course, it will not invert my transformation in general, right? So basically, I would like to compute so in algebra, the general name for transpose is called the adjoint operator. There is slight difference when we talk about complex sequences and complex operators, but we care about real valued functions only, so there is no difference between adjoint and transpose. And the adjoint operator, the formal definition of the adjoint, so suppose we have a map A from space U to space V. I'm assuming that the spaces are equipped with inner products. So the adjoint, which is denoted by A star, or A transpose, if you will, is a map from V to U. So the domain and the codomain of the map are reversed. And it has to satisfy for every x and y, the inner product of ax and y, obviously computed in V, is equal to x inner product with A star y, obviously computed on U. Okay, and this has to hold for every x and y. This is the formal definition of a transpose, of an adjoint operator. And just pay attention, despite the inversion of the domain and the codomain, A transpose is not an inverse. A is typically not invertible, at least in our case. The cases where where A transpose equals to A inverse is called unitary transformation, right? It's a rotation matrix. But generally, there is no connection between inverse and transpose. So I would like to embody the layers, the convolution layers of the decoder as the adjoint versions of the convolutional layers of the encoder. Okay, so I will reverse their order, and for every convolution layer, I will have an adjoint convolution layer in the decoder. And a very poor name in the literature is called deconvolutional layer. So when you say deconvolution, for example, if I have some system H acting on X, this is convolution, right? When in signal processing you say deconvolution, you care about this, right? You want to invert the action of a convolution. Now, this is not an inverse. This is a transpose. This is a joint. So it's not deconvolutional. It doesn't do deconvolution. It does a joint convolution. Okay, so let's use this terminology properly. So again, this is the linear part of a convolutional layer. I will keep the same nonlinear part. The linear part does this, right? It does convolution with some set of weights W. Okay, and the set of weights W, of course, had a certain dimension. You see, you have this K and L, L going from 1 to M, K obviously from 1 to N, right, in our notation. Now, I would like to compute the inner product between AX, the output of this convolution, and some new signal Z. Okay? Just pay attention, we have a d-dimensional sequence of n-dimensional vectors, right? So this is the standard way of defining inner products. So it will be the sum over my index, d-dimensional index, of the regular inner products between the vectors. So if I spell it out, there will be two sums, one over j, my spatial index, and another one over k, which is my feature map index, my channel index. Okay? This is how the inner product is defined. This is the standard Euclidean inner product. And let's write it explicitly. I'm substituting, instead of the first argument, I'm substituting what is written here. Okay? Simple algebra. Let's reindex this sum. So obviously I would like to obtain another inner product that has x free and something acting on z. Okay, and I would rather have this something looking like a convolution. Okay, so this is my objective. This is what I'm trying to do. So let's reindex. I will call j prime, I will call it pj. So I would want to get rid of this pj. So let's reindex the sum. Then j will be j prime over p, which doesn't fall into the integer lattice anymore, right? It doesn't have integer coordinates. So let's define this expansion or this upsampling operation by p. We saw it already when we talked about dilated convolution, right? So I'm going to from a sparse lattice to a denser lattice, I'm going to retain my samples where my denser lattice coincides with the points of the sparser lattice, and I'm going to put zeros elsewhere. Okay? So it's exactly what we did when we talked about dilated convolution. Now, in these terms, I can write what is written here with the new index j prime. The sum here will be over j prime. And instead of z, I'm going to write upsampled z by a factor of p. Okay? Make sense? So let's again do some reindexing. Instead of j prime minus I, which is written here, I'm going to write a new index j prime prime. Since j prime goes over the entire integer lattice, j prime prime will also go over the entire integer lattice, right? So the boundaries of this sum are going to be the same. So this is my new index j prime prime. So you see, this x already came out with this index j prime prime. And what I have inside, I'm starting writing it in blue, I have here j prime prime plus I. So you see, this blue term, I also changed the order of sums. I have k, sum over k inside and sum over L outside. So I would like to interpret this blue as the action of some linear operator and what is written outside as an inner product. Okay? Now, what is written here almost looks like convolution. What prevents it from being a real convolution? We don't, but in convolution, we should have a minus here, and we have plus. So let's just do the following. I will define W bar, a new set of weights, which will be simply defined as W with index minus I. So I'm mirroring my filter with respect to every axis. Okay? And now in these terms, I have a convolution. This is going to be a convolution. So what is written here is a convolution, and this is the action of my adjoint operator, because what is written outside is an inner product, right? So basically what is written here is an inner product between x and a adjoint z. Okay? So now I have the form for the adjoint operator. This is, by the way, this is the formal way of getting adjoint operators from any linear operator. You just write this inner product and you rearrange the terms until you get another inner product where the second argument is acted upon by some operator, and then you declare that operator as the adjoint. Okay? So this is the form of my adjoint operator. So the input is what used to be the output of our convolution layer in the encoder. The output is of the same dimension of what used to be our input, and we are doing this adjoint strided convolution. So in regular strided convolution, we first did convolution, then downsampling. In adjoint strided convolution, we first upsample the input sequence and then do convolution. Okay? This is what adjoint does. Now pay attention that this is not equal to dilated convolution. So adjoint strided convolution first upsamples the input sequence and then does convolution with W. Dilated convolution upsamples the kernel W and then does convolution. Okay? Completely different things. Even though they look similar in notation, they are doing completely different things. Okay? So we know how to transpose convolutions, right? So we know how to create these symmetrically looking convolution layers. Some people in some architectures also like doing pooling between the convolution layers. So a pooling, suppose we have this input sequence X. I'm assuming it to be scalar valued because pooling is usually done channel wise. So for each channel I'm going to do a pooling. I will define a p pooling that takes a window of p in every direction, so p to the power d input samples, and maps them to a scalar. Okay, so this is my p pooling layer. And for example, we have max pooling, taking the maximum over the window, or the average pooling, taking the average over the window, or just subsampling, taking the central element, for example, of this window. And then we produce this sequence y. Of course, pooling also reduces dimension by the factor of p in every direction, right? So let's see how we do unpooling. How do we do adjoint pooling? So the adjoint pooling obviously will be a map from this y to windows, right? So every y will correspond to a p by p by p by p window, p to the power d samples, right? So with max pooling, again, I'm not going to waste your time on doing the formal computation of the adjoint, but you can try doing it yourselves. With the max pooling, I will simply, when I do the pooling itself in the forward direction, I will keep the index of the arg maximum, so the index where I found the maximum. And then when I do unpooling, I will fill the window with zeros, and that location that gave me the maximum will be filled with the maximum value. Okay? Well, it's not padding by zeros because the location of my non-zero sample depends on where it was selected from in the original pooling operation. Mm-hmm. So, for example, if this was my sequence out of which I selected this sample, in the pooling direction, I retain this sample only, right? So this entire window was mapped here. When I do unpooling, I'm going to place this same value and the same, basically, and the values around will be filled with zeros. Okay, so this is the max unpooling. With average pooling, well, I took it from the pooling, so so these are symmetric operations. So I will remember which value I took in the pooling step, and I will use it for the unpooling step. Okay, so they always work together. In the case of average pooling, well, again, I'm talking about a very specific architecture of having encoder and decoder side by side, right? So whatever was transformed by pooling on the encoder side will be transformed by by symmetrically looking unpooling on the encoders, on the decoder side, and then I can basically retain this arg maximum. Well, but still, I can build this. I can build this in the setting where the encoder and the decoder work together. I'm not suggesting that pooling should be used at all in CNNs in general. I think strided convolution already does a great job, and it is much easier to, for example, to differentiate. Okay, but if you were, for example, want to do average pooling, you are just filling the window with the same values that your input scalar gave you, right? So basically, you're going to, when you do pooling, you average the content of the window, and when you do unpooling, you just produce a window of the same values replicated over the entire window. Okay, so these are the formal adjoints of pooling operations. But in general, I think CNNs for encoder and decoder architectures, CNNs without any pooling, just strided convolution and adjoint strided convolution, they do marvelous job. Okay. Any questions? So basically, currently we have constructed a typical architecture for convolutional encoder-decoder networks, for convolutional autoencoders. What we are going to see next time is actually how to train generative models. How do we train a model that will allow us to sample new data from the structure of the data we learned by unsupervised training? And we'll see with the formalism of variational autoencoders that first of all we will need to formalize the unsupervised setting in the probabilistic notation, and then we'll see how we create a very elegant way of building meaningful distributions in the latent space from which we can sample new points. Okay, so this is something we are going to see next week. I would like to resume from the point we stopped 2 weeks ago. So I remind you that we start talking about unsupervised learning, and by unsupervised learning, I mean a scenario where we want to discover the structure of the data without the need to regress on the label. So we are not trying to predict a label from an instance. We are just trying to discover how the instances are distributed in the instance space. So our departing point was by claiming that though the instance space might have some huge dimensionality, like the space of all images, for example, the data inside that space, the relevant data, the data that interests us, will typically have some lower dimensional distribution, something that has a smaller number of degrees of freedom than the dimension of the embedding space. Okay, this was the premise under which we started talking about unsupervised learning. And I remind you that I showed you a very trivial example, basically a PCA, a linear subspace model. We tried to model our data by a linear subspace. It has a closed form expression in terms of an SVD of the data matrix. Unfortunately, real data do not really admit, or at least not accurately, do not really admit linear models. So our next model was something that we called an autoencoder. So we start with our instance space. We take a data point x in this space, and we transform it by a map that we denoted as psi. We called it an encoder, into some latent space z. So here is the image of this map. It produced a point z in this space. So this is the image of the point x. Okay? And then we want to transform this point z by another map, which I called psi, and we named it a decoder. And we want this point, of course, this point will be a point in the instance space, and we wanted this point to be as close as possible to the point we started with. So essentially, we would like the composition of the encoder with the decoder to be as close as possible to the identity transformation, right? And obviously, we we model these maps phi and psi by using neural networks, right? So this is our class of models. They can build very complicated nonlinear maps. Obviously, you can say that if indeed your model capacity, basically your capability to represent different nonlinear maps is so great, then what's the difficulty in getting an identity map? You just build any phi, and then you build its inverse, and you get an identity map. This is basically, there is nothing interesting happening in this process. But then we said that we wanted the dimension of z to be significantly smaller than the dimension of x. Once you do this, you created a bottleneck. So some information is lost in this map, because z now restricts your representation to be something narrow, something low dimensional. And then the whole point of this exercise is to discover such a representation or such a pair of encoder-decoder functions that will, of course, lose information, because this is what the dimensionality commands us to do, but it will keep the maximum amount of essential information to reconstruct the point, the instance x, as faithfully as possible. And that was our setting. We discussed how to build a convolutional autoencoder. So it's obvious how to build using strided convolutions, how to build an encoder that reduces dimensionality, right? And then we discussed how to take the adjoint of this structure, how to take the transpose of these operations to build a decoder, something that takes a low dimensional input and produces a higher dimensional input. Okay, so that was our convolutional autoencoder. It's a technical detail, but we needed to actually build real autoencoders. So today I would like to focus on this very essential question. Otherwise, all the exercise is not really worthwhile our attention. So how do we generate new instances using this model? So I stated this from the beginning. I want a generative model. I want a black box. I hit a button, and it spits out an image, something that looks like an image. Okay, so I want to generate new images, and I want them to look like images, right? So this is the whole point, the essence of a generative model. So in our model, we represented images or whatever instances that we have in our problem as points in this latent space. So whatever lives in that latent space will be a meaningful instance, right? At least hopefully, if we did the learning correctly. So essentially, any point I'm taking in the instance space will give me a data point on that latent data manifold that I discovered in this way. So it's not only a way to discover the structure of the data, it's a constructive way to discover the structure of the data. I can now generate new points on my data manifold. Okay? So my question is actually, how do we sample from this model? I would like to create new samples. I would like to generate new instances. So in this latent space, we have some distribution, maybe very complicated distribution, according to which the data are represented in that latent space. Okay? And I would like to sample a point from that distribution and pass it through a decoder. This map is a decoder, right? This is a decoder. And this will give me a new instance. Okay? Now, however, sampling from something crazy that might arise here as the distribution in the latent space is not necessarily very easy. Right? Even think how we model this distribution, not so easy. Z will be a high-dimensional space. Not as high-dimensional as the data space, but still very high-dimensional. So let's slightly switch our optics. So before we thought of everything as deterministic quantities, I would like now to give you a view on this construction from the probabilistic point of view. Okay, so from the point of view of statistical estimation. We did it already with our supervised models. So let's see how encoder and decoder appear from this probabilistic point of view, and then see how this leads us to an efficient and powerful way of building generative models that we will name variational autoencoders. Okay. So our decoder was a map psi from Z to X. So I'm trying to keep some consistent color code. Instances will be orange, and representation, latent representations will be blue. Okay. So our input, I'm assuming that my input is a random quantity, is a random variable Z, distributed according to this probability density P in the latent space. Okay? So I can think of this as a prior distribution. Okay? This is my representation. Okay? My output, I will think of my output X is my instance X, is also a random quantity. Again, pay attention, this is a random quantity. Before, in our view, it was just a deterministic output. I would like to think of it as a random quantity. Of course, this is a superset of what I can get with deterministic quantities, because if I make this distribution a delta, it will be giving me deterministic quantities, right? But in general, it is a probability density function of X conditioned on Z. So you pick your representation in the latent space, and this representation, given that representation, generate me an instance. Okay, so I'm assuming here this probability, this conditional probability density is called the likelihood. Okay, it's in the Bayesian jargon is called the likelihood. I will do the following simplifying assumptions. By the way, we are not going to lose generality. So I told you that the distribution of Z in the latent space can be arbitrarily crazy, right? Can be very complicated. But just imagine how we obtain this Z. So we have our original instance space X. We put an encoder here, right? This is an encoder. And we produce a representation Z here, right? So I started with some distribution, let's call it Px, and I ended with representation Pz. Well, actually, it will be Pz given X, but let's think of an unconditional distribution here, the marginal. It can be arbitrarily crazy, right? Now, can you turn this crazy distribution into something very easy, like the normal distribution? I claim that put a sufficiently complicated nonlinear transformation here, and you will get a nice normal distribution here, okay? Do you agree? I can transform any arbitrary distribution into something normal or something uniform, anything you like, right? So this could be a completely crazy transformation, but let's absorb it into the encoder. Okay? The encoder is already crazy enough to map instances to this representation space. So let's just make it slightly crazier, and we'll assume that its output is normally distributed. Okay? We'll just absorb that additional nonlinear transformation into the encoder. So this is my assumption. Normally distributed with zero mean and identity variance. Okay? Now the output of my model, again, I said that this likelihood is in general is some non-trivial probability distribution function. Let's assume that it looks like a point and some noise around it. So in our deterministic view, it was just a point. So let's add a noise around it, and I will assume that this noise is again isotropically Gaussian, isotropic normally distributed, with some hyperparameter sigma here. So this sigma measures how much uncertainty I have in the generation of my instance once I'm given its latent representation Z. And this sigma is some hyperparameter in my system. Okay? We will see that it can be interpreted as some regularization, the strength of a regularization term. Okay? So again, I am assuming that my prior distribution is normal, and I'm claiming that the encoder will ensure it. And I'm assuming that my likelihood is also normal. Of course, all the complexity of the model goes into this mean. Okay, so the mean is a complicated nonlinear function of Z, parameterized by this parameter beta, and there is some noise around it that I'm allowing for. Okay? Everyone agrees on this model? So that was the decoder. Let's now see how we can think of the encoder from this probabilistic perspective. So the role of the encoder is to infer the latent variable z. So the encoder, remember, encoder gives us the map from the instance space x to the latent space z. So we would like to infer the representation z, the vector in z, given an observation of the instance x. Okay? And of course, we can think of it in the terms of Bayesian inference as the encoder will be modeled as a posterior distribution of z given x, right? So you give me x, your instance, and now I'm telling you how your representation will be distributed. So again, z is a stochastic quantity. It will give me a distribution of z, hopefully narrow enough, so it falls into some very tight cluster in the representation space. But I'm by building an encoder, I'm trying to build this posterior distribution. The posterior distribution obviously is given by Bayes' theorem that relates the prior, the likelihood, and px, which is in Bayesian terminology is called the evidence. Okay, evidence is the data that we observe. Okay, and from what is called the total probability formula. So basically, in order to compute the posterior, in order to build the encoder, I need the likelihood, I need the prior. I have them both, right? So the likelihood is what the decoder does, plus some noise around it. The prior, we assumed simple normal prior. And the evidence can be obtained by this total probability formula, right? So I will just integrate the likelihood, which is conditioned on z, integrated with the density z over all z's, right? Trivial probability. Okay? Now, can we actually compute this? Why not? Well, so it's not that we don't have the likelihood. The likelihood is our model, is our decoder. So we are going to learn it. So given px, so you give me px given z, can I estimate this evidence distribution? Now remember, so basically we need to estimate a density function. Z is a high-dimensional space. So in order to estimate it correctly, you will need a zillion of samples to estimate it faithfully. Okay? So it's really hard to estimate densities in high-dimensional spaces. You suffer from what is called the curse of dimensionality. It's very hard to estimate anything in high-dimensional spaces. So you can estimate something in high-dimensional spaces. Basically, all our learning problems are about estimating functions in high-dimensional spaces, just because we know that we only care about these estimates to be accurate on data that admit low-dimensional distributions, right? There is no chance to estimate functions that really take inputs from some isotropic Gaussian distribution, for example, even in dimension 10 or dimension 50. So it's really intractable to estimate this, or we will need a hell lot of data, and then it will be intractable computationally, because we will need to write this as a sum on, I don't know, a few billions of data points. Okay? So this is really intractable. Yes?
So just to make sure, why was the problem?
The problem is this integral. The problem is that you need lots of samples to estimate this integral. So you need to estimate a density. Instead of an integral, you will write a sum. This sum will be accurate in high dimensions. In order for it to be accurate in high dimensions, you will need really, really many samples. Okay? Of course, you can estimate it, but it's impractical. So we'll see. Let's see how to circumvent this problem. So this is what I'm trying to lead to. So again, let's ignore for now this unpleasant fact that we have a model that we cannot treat in any practical sense. Okay, but let's ignore this for a second. If you agree with this model, we have a very simple way of generating new instances. So I first sample my z from the prior distribution, okay, which is just generating an isotropic random Gaussian vector, right? Very easy. Then I will sample x from this px given z, which is again sampling from a random Gaussian distribution. But the way I'm going to write it, I will transform my z by this crazy nonlinear map with the parameter beta. This is the map I'm going to learn, right? This is my decoder neural network. And then I will add to it some isotropic Gaussian noise, okay, with this hyperparameter sigma. This is my generation, okay. Now you see that the encoder-decoder architecture is no longer evident in this construction. Where is the encoder? I have a generator that works in the latent space, and then I have a decoder that produces an instance. So I actually tossed away the encoder. I really care about being able to generate samples. So why do I need an encoder? I just need a way to map from this latent space to the instance space. Okay. So again, this is a way to generate new samples. Okay. So I would like to generate new x, but I would like that x to be, of course, to reside in my subspace of the instance space. So instance space might be of very high dimension, but I would like something that has the structure of my data, right? So I would like to discover that structure from a finite sample, that is my unlabeled training set, and then I would like, once I did that, I would like to be able to generate new data points. Okay, so this is the purpose of a generative model. Yes. We can do many things, but basically it will be for simplicity. I'm just assuming that somebody gave me this as a side information. This parameter will essentially be controlling the amount of regularization we are adding to our unsupervised loss function. Okay, so we can interpret it this way. And usually, of course, such parameters are selected using cross-validation. Okay, so if you agree with this generative model, so what is our purpose? How do we learn this generative model? We have a training set. We have some set x1 to xn, right? So these are the actual data, but that somebody sampled from that latent data distribution px, right? From that evidence distribution. And we have a model for the evidence, right? We have it. We don't know how to calculate it, but we have that model, right? Once we know these things, we can actually estimate the evidence, right? And then we can try to maximize it. Let's maximize this. Let's build such an evidence. Let's basically, by selecting this parameter beta, let's build such a probabilistic model of the evidence from which the data could actually have been sampled. So we'd like to maximize the probability of the actual data that we received, right? And I'm assuming that our data are sampled IID from that distribution, so I can write this joint probability as a product of the marginals of each individual data point. And of course, remember that our px is given by this total probability formula, the integral over the prior probability of the likelihood. Okay, the likelihood contains all the intelligence of our model, and the prior is just some stupid normal prior, because all the complexity goes in this likelihood. Okay, so then I can maximize the sum of the logs, or minimize the sum of the negative logs. Okay, because the product conveniently becomes the sum of the logs when I do a logarithmic transformation. Okay, so I would like to maximize this sum. I can define my loss function. So when I'm talking about loss function, I'm minimizing the loss function. So this will be just the sum over my training set of point-wise losses, and the point-wise loss here depends only on a single data point, xi. Okay, and I'm summing these losses over the training set. We know that by the law of large numbers, when n goes to infinity, this empirical average approaches the expectation of Lx over x, right? So this is actually an expectation over that px from which the data came and that we are trying to model, right? We're trying to build a model for this probability distribution. And the pointwise loss will be simply the negative log of the evidence probability. So because we like working with loss functions and minimization of loss functions, I have the minus sign in front of the log. Okay? Just to be consistent with our notation. So instead of a maximization problem, I have a minimization problem. Okay, and of course this is the negative logarithm of this integral, right? Which is still intractable. We don't know how to compute it, at least not practically. Okay? Makes sense? So if we knew how to model this probability, we could train by minimizing this loss. That would maximize the evidence probability. So it will find a model for the evidence probability that describes the data, or basically that makes the data maximally probable, and we'll be able to then to generate samples from this probability distribution according to the scheme that I described a few slides ago. Okay? So let's see how we treat this intractable probability distribution. And basically, this is obtained by a scheme that is called Variational Autoencoders. It's a very clever idea, and I will show you some details now. So what I will do, basically, estimating this evidence probability is like estimating the posterior distribution, right? Because the posterior distribution is given by the prior, the likelihood, and the evidence in the denominator, right? So if you don't know how to estimate the evidence, you don't know how to estimate the posterior. If you know how to estimate the posterior, you have the likelihood and the prior, you know how to estimate the evidence. Okay? So I'm going to model the posterior. The actual probability distribution PZ is intractable because it requires the evidence and the denominator. I'm going to replace it by a model, by this model Q alpha. It's a parametric model. Every time you hear the word parametric model, think of a neural network. Okay, so it's some crazy neural network, might be very complicated, that receives X. It receives X and gives you the distribution of Z given X. Okay, so it looks like an encoder, right? This is how we model the encoder. So it gives you the distribution of the latent representation given the instance. This is what the encoder does. Okay. So I'm going to model this posterior distribution. And the typical choice, again, we said that the encoder will ensure some simple distribution. Let's ensure this simple distribution. I will model my posterior as a normal distribution with some mean vector mu alpha. Okay, so alpha is a parameter. And some covariance, typically a diagonal covariance, which is given by, the diagonal elements are given by the vector sigma alpha. Okay? So again, mu and alpha are two very complicated transformations of the instance point x. So you give me the instance, I do some hard nonlinear crunching with many, many parameters alpha. This is my neural network. And I'm outputting you two vectors of the dimension of z. Some dimension k that we established by hand. Basically, these two vectors tell us tell us the posterior distribution of z given x. Okay, we're assuming this normal model. Sure, please. Okay, so the question was why isn't z given x a deterministic quantity? Sure. Z given x. So you give me a vector, a deterministic vector of your instance. Why is it a distribution and not basically a delta, right? Something like that. So first of all, when we work in this probabilistic setting, I'm thinking of everything as distributions, including deterministic quantities. A deterministic quantity is also something that has a simple singleton distribution. So I can make this sigma alpha to be very small. If this is the best description of my data, sigma can become very small. Okay. So you will see the trade-offs actually introduced by the hyperparameter sigma squared that we had on the noise of the generator. So the more the noise will be there, the less we are going to demand exact fitting of the data. Okay, so again, you will need to see the actual expression. Okay, but basically we'll have some trade-off between regularization and fitting of the data. But again, I'm thinking of everything stochastic or deterministic as a stochastic quantity. Okay, any other questions? So again, I'm approximating the posterior by this model Q alpha. So remember, we have now two models. One model for the likelihood, parameterized by beta. That was our decoder, right? And another model is for the posterior, and we think of the posterior as an encoder, and it has a different parameter, alpha. Okay, so two sets of parameters, two neural networks. Now, of course, this cannot be just any distribution, obviously, right? It has to be something that has to do with the actual distribution of the data, or the posterior distribution of the data. So I would like to ensure that this Q alpha is indeed an approximation of P, z given x, of the actual posterior. How do I do this? So I have two objects. One of them is the actual distribution, which you cannot compute, right? Because if you could compute it, you could compute the evidence.
Use the normal transformation.
No, but wait a second. So I just have two mathematical objects. This is something that is under my control, and this is something that hopefully I can estimate from the data. We know that we cannot, but maybe I can estimate something related to this quantity. But if I could estimate this quantity, I could write a distance or a divergence between these two quantities and measure how far one is from the other, right? This is exactly what I'm going to do. I will write a distance. I cannot show you quotation marks. This is not exactly a distance, okay? But this is some discrepancy between these two objects, right? So one object is under my control, another object is not under my control, okay? And what is the typical way of measuring the discrepancy between two probability distributions? There is one canonical way that is called the Kullback-Leibler divergence, which given P and Q and know that there is no comma separating between the two distributions, but actually these two bars, because this is not a symmetric distance. dP given Q is not dQ given P. It's not symmetric. It's not a metric. That's why it is called divergence and not distance, because distance usually we say distance, we think of a metric, something that obeys symmetry and triangle inequality and so on. So the Kullback-Leibler divergence is simply the expectation of the negative log of dq over dp, expectation over q. And this ugly thing is what is called the Radon-Nikodym derivative. If you don't like the Radon-Nikodym derivative, it's just, you can write it in terms of probability densities as the log of the ratio of two density functions. Okay, but the exact formulation is using the Radon-Nikodym derivative, and we can plug this Kullback-Leibler divergence here. So it will be the expectation of z drawn from q alpha. Okay, so the first parameter is q alpha. I'm drawing z from q alpha, which is nice because this is something that is under my control, of log q alpha minus log p. Okay, this is the log of the ratio of the densities. Okay. So now let's substitute. I have this P, which is the actual posterior. So the Q is a model for my posterior. It stays as is. This P, I can substitute the Bayes theorem, right? What is written here is the Bayes theorem, just for log densities. So instead of having a fraction, I have a sum and basically a sum of the terms in the numerator and minus the term in the denominator, right? And I'm substituting this into the expectation, right? So everything, this term and this term depend on z, and this term doesn't depend on z. So I'm writing it outside the expectation. Doesn't depend on z. Okay? So let's write it explicitly. We have the Kullback-Leibler divergence between Q alpha and the actual posterior P equals to the expectation of these three terms plus this log term, Px. Okay? Let's rearrange the terms. So basically, I care about log px, obviously, right? This is the quantity I would like to give expression to. So it's this log px minus the Kullback-Leibler divergence between q alpha and p, which equals to this expectation of, I'm writing this as the expectation of, basically I'm splitting it into two expectations. The expectation of log p x given z, which is our likelihood, right? This is likelihood, minus what is written here. Now, what is written here is the expectation of over z drawn from qa of the log of ratio of qa over pz. Sounds familiar, right? So what is this expression? It looks like the KL divergence, right? Of which two densities? So it's the divergence between Q alpha and P, right? The prior. So what we have again is the expectation over QA of the log likelihood minus the divergence between Q alpha and P. Now P is simple. It's simply normal. Q is also normal and it's fully under our control. So this term is perfectly tractable, right? This term is also tractable, at least seems, because there we have our decoder model. Remember, this px given z was normal with actually mean controlled by the parameter beta, right? And here, this q alpha is controlled by the parameter alpha. So we have two parameters that we need to learn. Now, what makes this expression intractable is obviously this part, right? Because again, we cannot compute the Kullback-Leibler divergence of q alpha, which is under our control. But we have, again, this posterior, the actual posterior. In order to compute it, we need the evidence in the denominator, and we cannot estimate the evidence. Okay? So this is still intractable. But let's remember, so what is exactly this term? Why did we have this term? Okay, so this term was to ensure that q alpha is actually an approximation to the posterior. So it is small. Okay, so first of all, it's strictly non-negative, because the divergence is strictly non-negative. And it is small. Otherwise, it's not a good approximation, right? So let's just drop it. So if we don't know how to treat it, let's drop it. And then we don't have an exact expression. We have an inequality. We have what is called the evidence lower bound. We have a lower bound on the log density of the evidence probability. Yes? So the proposal was to actually take that big integral over pz and or the log of that integral, and you use Jensen's inequality. But still, you will have that. To get it accurate, you will need to replace this integral or whatever goes inside the log, or the integral of the log, or the log of the integral, with a sum over a very big number of samples. So it doesn't change anything.
No, but then you can do empirical estimation like any other.
Of course, you can do, but empirical estimation in a high-dimensional space is very problematic. That's the difficulty, not the order of integration and the log. That's the real difficulty. It's very hard to compute an empirical density model in a 50-dimensional space.
What is it? If the integral is inside the log, you need to compute a lot of examples to just get one update. But if the log is inside the integral, you can make a lot of updates. And
the order doesn't matter. The order doesn't matter. You still need lots of samples. Okay. So basically, what we have is called ELBO, the evidence lower bound. So we just dropped this term that we want to be small anyway, right? So we have a lower bound on the log evidence density. Okay? And now on the right-hand side, everything is computable, everything is tractable. So let's see how this leads to our unsupervised loss function. So our loss function, I remind you, was the empirical average of these pointwise losses, which we set to be the negative log probability of the evidence of each data point xi, right? So this sums, of course, over the entire training set. Now let's substitute. We don't have negative log px. What we have is So it was lower bound on log px, it's an upper bound on negative log px. So we have an upper bound to this quantity. So let's denote this upper bound by L bar. Okay, so I will just think of it as our actual loss. So I cannot compute the actual loss, but I can compute its upper bound. Let's just compute its upper bound. This upper bound, let's call it by L capital bar. If I minimize my upper bound, hopefully if the bound is tight enough, the actual loss will also be small. Okay? This is a trick that is done very often in estimation problems. So you don't know how to compute the actual function, but you can upper bound it by something and minimize this simpler expression for the upper bound. Works well when it works well. Okay? And here it works well. So of course you need some way of telling the accuracy of your bound, but here we have a good control over it. Okay, so this is our pointwise loss that we would like to minimize. Okay, so let's substitute. We have three ingredients to this loss, right? We have the prior, which is simple normal prior. We have the likelihood, which is our decoder model, okay, with the parameters beta. This can be a complicated neural network. This is actually a complicated neural network. And then we have our model posterior. Let's call it model posterior. It's not the actual posterior. This is our approximation by another neural network that actually splits two outputs. One is mu, another one is sigma. So I'm writing here a full covariance matrix. In practice, this would typically be selected a diagonal covariance matrix just to reduce the number of parameters. So we can substitute this into the expression. Fortunately, then that was the reason why I insisted on Gaussian distributions, on normal distribution, not something else, because there is a very simple closed form expression for the Kullback-Leibler divergence between two normal distributions. Okay, this is something that you can simply look up or derive yourselves, not difficult. So this first part, you see, it will be the normal distribution with mu alpha as the mean and sigma alpha as the covariance, and this is the canonical normal distribution with zero mean and identity covariance, minus expectation over QA of log this normal likelihood function. Okay? So if I evaluate these expressions explicitly, the first term here, this is my Kullback-Leibler divergence. Actually, Kullback-Leibler divergence always gives rise to these minus log det expressions. Okay, so it's minus log determinant of sigma alpha, trace of sigma alpha, and the Euclidean norm of the mean vector squared. Okay, and the second term, when I take the negative log of this Gaussian density, I just get 1 over twice sigma squared, because we have this diagonal covariance matrix with sigma on the diagonal, sigma squared on the diagonal, and of course the Euclidean norm squared of x minus the mean vector, which is this psi beta. Okay? So we have a very simple expression for our upper bound on the pointwise loss. Okay? Questions? Was some question here? No? Question? Yes. Okay, so this is a very important point. So let's make an attempt at minimizing this, right? But you actually are raising a very important point. So the point was basically, can we actually split the minimization into minimization with respect to just alpha and just beta? Looks like the function is separable, but it's not exactly separable because this expectation depends on alpha. Okay, it's very important. If it didn't depend on alpha, then it would be perfectly separable. So we have this. We have our loss, which again is the expectation of the pointwise loss, or the empirical estimation of this expectation on the training set. I'm dropping all those 1/2 constants, so there will be some proportion coefficient. Here doesn't really affect our minimizer, obviously. The first term comes from the Kullback-Leibler divergence. The second one comes from the expectation of the likelihood, right? Plus some constant. So let's take the gradient of this expression. Okay, so it will be the gradient with respect to our parameters. Alpha and beta are our parameters, so I'm writing the gradient with respect to both. Okay, and we know how to minimize such functions, right? Let's do one step of stochastic gradient iteration, right? So we sample one point and do a stochastic gradient step. Okay, so let's do it. Let's sample x from the training set. So x essentially sampled from the actual data distribution or some finite sample approximation thereof, right? So this is the data distribution that I have access to. Then let's sample z from q alpha, my current model for the posterior q alpha. Okay. So I have a single sample, and let's now compute the gradient. I will just substitute these x and z's inside my expression here, right? So it's a single point, and let's just compute the gradient. Of course, I can exchange the order of gradient and expectation. This is what I always do in stochastic gradient, right? So that's why I first sampled, then took the gradient of the expression. Okay, makes sense? So now I will use a slightly different color scheme. I have two expressions here. One expression that depends on alpha. Another expression that depends on beta. So let's deal with alpha. So what is written here, this delta alpha is actually in our notation, this is the derivative of the loss with respect to the parameter alpha, right? So it's just given by the chain rule. What depends on alpha is mu and sigma, right? So it's delta sigma, which is the derivative of the loss with respect to sigma, times the derivative of sigma with respect to alpha, plus we have the loss depending on mu, right? So it's delta mu. Again, this is dl over d sigma, right? And this is dl over d mu, right? And of course, it's L bar everywhere because it's not the actual loss, it's the upper bound. Okay? So we can write this explicitly. Actually, this is a very nice expression. How do you find derivatives of minus log det? So you open a reference that is called Matrix Cookbook. You find every imaginable derivative of matrices or vector expressions or functions of matrices. So one of them is negative log det. It will give us minus sigma inverse. Okay, and the term I here comes from the derivative of the trace. Okay, so the trace gives I, the identity, and minus log det gives minus the inverse of sigma. Okay, plus the second term, of course, this Euclidean norm will just give 1/2 d mu transpose over d alpha times mu. Okay, so the inner derivative here will be 1/2 mu. Okay, so if I assume now that sigma, so you see the nasty thing here is that sigma is a matrix and alpha is a vector. So what is written here, this expression is a rank 3 tensor. If I now assume that my sigma is a diagonal matrix with some vector sigma on the diagonal, of course sigma function of alpha, of the parameters alpha, I can now write it in a simpler form. Trust me or just follow my math. Okay, so this is my expression for the gradient of the loss with respect to alpha. Okay, very simple expression. Now the same about beta. Beta is just finding the derivative. So basically, again, this is the derivative of the loss with respect to psi. Okay, which is this expression. This is psi, this vector psi. And then the derivative of this vector psi with respect to the parameter beta, which is computed by backpropagation, of course, because psi beta is a neural network. Okay, so just finding the derivative of psi, the loss with respect to psi. This is my loss, right? And this is how this derivative looks like. Just the derivative of the Euclidean norm squared. Okay? So this is my result. So again, how do I do my stochastic gradient step. I sample x from my data, from my data distribution. Okay, and then I sample z from QA. So it's not given z from px. Okay, from the actual data distribution, I sample z from my Q alpha, sorry, and then I compute this derivative. Makes sense? Something is wrong here. Can you see what is wrong? So you see, we have this expression depending on z, right? And how did we obtain z? We sampled it from a distribution that depends on alpha, but we don't have any dependence on alpha here. So somehow this dependence on alpha disappeared. Because that dependence was because we had an expectation with respect to the density Q alpha. When we took stochastic gradient, we dropped that expectation because we just sampled one point, but that dependence still exists, right? So we don't really, so we can easily do backpropagation on everything that I wrote here, but we don't know how to do backpropagation on this. So we have some stochastic layer inside the network. It's very easy to deal by using backpropagation and stochastic gradient. It's trivial to deal with a stochastic input to the network. But the operations that the network performs have to be deterministic. If they are not, we don't even, even the notion of the gradient doesn't exist anymore, right? So basically what we have is some kind of a stochastic layer that samples z from this model posterior distribution. We don't know how to take derivatives of this, right? So what can we do? So let's just pay attention how simple this distribution is. And just remember that for Gaussian distribution, if you do an affine transformation of a Gaussian distribution, it will remain a Gaussian distribution, right? So what we need to fix, we had this. We had z sampled from a normal distribution that depends on alpha, and alpha is our optimization variable. We have a stochastic quantity that depends on our optimization variable. We cannot treat that. We don't know how to treat that. Okay? So I want to do instead, I would like to draw some vector u from a normal distribution. This is still a stochastic quantity, but it doesn't depend on alpha, right? And then I will transform it by this transformation. It will be mu alpha of x plus square root of sigma alpha x times u. Okay? And this is a deterministic transformation that depends on alpha. So again, instead of having a stochastic quantity that depends on our optimization variable, I have a stochastic quantity that doesn't depend on the parameter alpha, and then a deterministic transformation that depends on alpha. So instead of having a stochastic layer, I have stochastic input to a deterministic layer. That is perfectly legit. Okay? So just do the math. It's obvious that what you get here, by basically doing this affine transformation, you are obtaining exactly this distribution, right? Just compute the mean vector and the covariance matrix, and you will get exactly what is written there. Okay? Any questions? Okay, back to our things. So basically what we did, we reparameterized our network in such a way that instead of having a stochastic layer, we have a stochastic input and a deterministic layer. Okay, so you can see what is going on here. Basically now the x is sampled from the training set, then we sample u from the canonical normal distribution, zero mean and unit variance, so it's just a random generator. Then you transform it affinely by the output of your encoder network, which is mu and sigma. Then you apply the decoder to this, and you want to minimize the distance from the obtained point in the instance space to the actual instance, right? So basically you sample your instance, you generated this random input, you pushed it into this loss function. Now the loss function is perfectly deterministic function on a random input. So the dependence on the parameters alpha and beta is perfectly deterministic, right? And then we can do we can do a stochastic gradient stuff. So let's just have another closer look at these loss functions. Of course, I'm just writing the point loss, but remember that we are taking expectation of this over our training data, right? Or empirical average on the x's, right? X's come from the training data. So what we have here inside is a generator. It produces points in the latent space. We decode them with our decoder, and this gives us an instance in the instance space. Okay? So this term is a data fitting term. It tells us how well this generated point fits the data. Okay? And this term, we can think of it as a regularization term. So this term actually came from measuring the divergence between the model posterior and the actual posterior, and we couldn't minimize that exactly. We could minimize an upper bound on that negative log posterior. Now pay attention to this quantity, 1 over sigma squared. We can think of it as a regularization strength because we have two terms. We have the regularization term and we have the data term, right? And the relative importance of one term with respect to another. So sigma basically controls the importance of the regularization term. The bigger is sigma, the stronger is regularization because it's 1 over sigma that multiplies the data fitting term. So remember, sigma was our hyperparameter that controlled the amount of uncertainty that we had in the generation of an instance given its latent representation. So the bigger is that uncertainty, obviously the less we should trust our data, right? Because this term embodies the amount of noise that we have. So the bigger is sigma, the more regularization we need. Okay, and so this is a way to interpret the expression that we obtain. Now let's discuss another important issue that is related to the choice of the norm. So we have here this Euclidean norm squared, which came from the negative expectation of the log of our normal distribution, but this normal distribution was just the expectation of the negative log of the likelihood, right? So this negative log likelihood gave the rise to the L2 norm, right? But again, this assumption of the normal distribution of the likelihood is purely pragmatic, right? Because this is something that we can easily optimize. So anything Gaussian with isotropic distribution leads to a Euclidean norm. And we like Euclidean norms. They are tractable. They have simple derivatives, and they are nice to work with. But there is no principled choice for this noise model or for this norm, right? Something completely arbitrary. So let's have a slightly deeper look at this. Maybe we can do something better. So I would like to think of my entire generative model. So remember, we sample a point U from the canonical normal distribution. Then we do this affine transformation that depends on the parameters alpha, and we obtain a point Z in the latent space. Then we feed it into our decoder psi, which is parameterized by the parameters beta, and we get an instance X. Okay? So I can think of this entire block, which is denoted here, as a single function. I will continue calling it psi, parameterized by some other vector of parameters gamma, which is simply a concatenation of alpha and beta. Okay? So this is my generative model. I push random noise into this model, and I'm getting instances. Okay? This is my generative model. Now let's do the following trick. I will take many data points, basically many realizations of this random noise, and generate data points. These are so-called fake data, because I never observed these data in reality. These are the data points that I generated. Okay? And then I will sample actual data, let's call them real data points, I actually sample them from my data distribution. So what this produces is some fake, let's call this P prime X. So this is not actually the real evidence distribution. This is some fake evidence distribution. Of course, we would like it to be as close as possible to the real one, but this is the entire goal of learning, right? So we want this distribution to be as close as possible to the actual distribution Px. But I can also sample data points, actual instances of data from the real data distribution, from the real Px. So I have instances of fake data and instances of real data. Okay? So some of them are real, and some of them are imposters, right? Some of them are pretending to be real. And I will say that I have a good generative model when I cannot distinguish between the two, right? If I cannot distinguish between fake and real data, then it's real for any practical purpose. Okay? So how can I distinguish between these two distributions? Let's build a classifier. Let's build a classifier that will receive data from these two distributions and will tell us how big is the probability that my data is real. So I will denote this discriminator by delta, parameterized by a set of parameters lowercase delta. Okay, and the output is the probability of the input being real or fake. Okay, so it's the probability of being real. 1 minus that quantity is the probability of being fake. Okay, obviously, if I'm now fixing P and P prime, the fake distribution and the real distribution, I would like this discriminator to give something that is very close to 1 on the real instances and something close to 0 on the fake instances, right? Make sense? So this is how I distinguish between the two distributions. So I will sample X from the training set. I will sample U from my uniform noise, from my normal noise, and generate an instance X prime using my generative model. Okay? And again, gamma is now my collective name for the parameters of the variational autoencoder, or actually it can be any autoencoder, not necessarily a VAE. So these are my parameters of the generator. So now I would like to maximize. I have basically the expectation on X and the expectation on U. So this is the real data. These are the real data and these are the fake data, right? So I would like delta X on real data to be close to 1, and I would like delta of my generated to be close to 0, right? So I will take log of 1. Log is a monotonically increasing transformation. So I will minimize the expectation of log of delta on my real data, and I want this quantity to be maximal, right? I want this to be maximal. And this quantity, I would like delta to be small. So 1 minus log of 1 minus delta expectation over the fake data would also be maximal, right? So then I maximize this loss function with respect to delta, to the parameters of the discriminator. This is how I train a classifier, right? So this is how I train my classifier. Given a generator, let's train a classifier that tells the generated data from the real one in the best possible way, best in the sense of this loss, right? And then what would you do? Then I would like to build a generator that, knowing that this is how we are going to distinguish between the real and the fake samples, will try to make this loss as small as possible. So basically, as bad classifier as possible. So I'm minimizing this over gamma. Okay? And this idea is called generative adversarial networks. So basically, I have an adversary that plays against me. And I would like, the adversary tries to beat me, to distinguish in the best possible way between my mistakes and their distinction from the real data. And I would like, knowing that I have an adversary, I would like to minimize the success rate of my adversary, right? So this is this min-max problem that I have. Another way I can think of it, I can think of what is written here as a loss function with respect to the parameter gamma. Okay? And now I am training my generator using this loss function. So instead of having that fixed L2 norm, I now have something that is much more complicated than an L2 norm. Moreover, this function changes when I change gamma. So it's some kind of a loss function that changes itself when I change my parameters. Okay, because it depends on also some. So from this point of view, this delta is just some nuisance parameter. I will of course try to make the performance of my discriminator as big as possible, but I can think of this as a black box. I give it a set of parameters gamma, and it gives me a number. Okay, so from this perspective, this is a loss function. Okay, and this is called generative adversarial networks. It was probably one of the most interesting and important innovations in the field of deep learning in the past 10 years, I would say. It gave a quantum leap of generative models. So now we can synthesize music, speech, images in a way that was never as realistic before. Okay, so if we are already talking about unsupervised training, let me show you one additional interesting and important training regime that we often encounter in real problems. So I would like to step one step back and show you how we can treat supervised training from this probabilistic perspective. And we saw some of this when we talked about neural network and logistic regression, multi-class logistic regression. So in supervised training, we have the joint distribution of the instance X. This is our instance X and label Y. Okay, that of course can be factored into the instance distribution Px and the conditional distribution of X given Y. Okay. Should be Y given X, obviously. Okay, Y given X. And we have a training set sampled from this joint distribution. So we have basically a labeled training set. We have instances, xi, and corresponding labels, yi. And our goal is to estimate this py given x from this final sample. Okay? So basically, if we think of it in deterministic terms, we would like what we call our target function. We would like a function that receives x and gives us the label y. Okay? So the way we can take an expectation over this joint distribution function of some pointwise loss. This is our pointwise loss that tries to give a prediction to the label. This is prediction of the label given the data point x. I will compare this predicted label to the actual label y that I have. Okay? And I will this basically y hat is a parametric family of functions. It's a neural network with parameters theta, and I will try to minimize this expected loss with respect to the set of parameters theta. Okay? And of course, in practice, I cannot evaluate the actual expectation. I will evaluate its in-sample approximation, right? And we discussed about why this leads to generalization. Okay. So a popular choice for this pointwise loss is the negative log of the posterior of theta given x and y. Okay. And of course, if I use the Bayes theorem, and I would like to keep, so I'm keeping x as my conditioning variable all the time. Okay. So it's a different probability distribution. It's a conditional distribution on x. So I would like to swap the order of theta and y, and by the Bayesian theorem, up to a denominator that doesn't depend on theta, so I don't care about it. It will be given by the probability of y conditioned on x and theta times the probability of theta conditioned on x. Okay? So just the Bayesian theorem. So think of x as some funny decoration of P. Okay? So this is my posterior, this is obviously the likelihood, and this is the prior on theta. Okay, so let's do it. Let's take the likelihood. Let's now take the likelihood. If we take the likelihood, so again, so if we minimize this posterior, we get a maximum a posteriori estimator. So we can think of our minimization of the loss function as a maximum a posteriori estimator of the parameters theta. Okay, and the maximum posteriori estimator, of course, comprises the likelihood term and the prior term. Now, pay attention. Prior term and theta on the distribution of the parameters. I'm now thinking of theta as a stochastic quantity. It has a distribution, and I would like to put some prior on this distribution. Okay, so I'm not telling you anything new. We'll see in a second. Okay, so first of all, let's take the likelihood. So the likelihood, I have some ground truth label that is generated from p theta y given x. So I'm assuming a family of distributions parameterized by theta, and just suppose that my class of hypotheses is so rich that the actual distribution of the data, so there is one set of parameters that I call theta that gives me the actual distribution of the data. So this is my distribution of the data. Okay? Or if you want to think of this deterministically, this is my target function, the actual target function. It's latent. I don't have access to it. What I'm trying to do, I'm trying to model this data distribution, this likelihood, by putting some other vector of parameters, theta hat. And as the result, I get a different label distributed differently. I call this my hypothesized label, y hat. Okay? Make sense? This is what I'm trying to do. And I'm measuring the Kullback-Leibler divergence between these two distributions, between the ground truth distribution that actually produced the data and the one that I'm trying to hypothesize. Pay attention, when I'm talking about the likelihood, I'm treating theta as a parameter. It's not a stochastic quantity in this discussion. That's why I'm writing it downstairs, right? Not as a conditioning variable, just to emphasize that this is a parameter. Essentially, my p theta is the output of the neural network. Right? When we talked about logistic regression, this is how we treated it. So I take the Kullback-Leibler divergence of these between these two distributions. This is how the divergence looks like. So I can write it as the difference of the expectation over p theta of log p theta minus the expectation on p theta, which is the actual data distribution, you see, of log p theta hat. This is what I'm trying to model, right? So this part is constant. And what I have here is the expectation on p theta of my negative log p theta hat. So when we encounter the cross entropy loss, this is how we obtain the cross entropy loss, right?
This is specifically for classification.
Specifically for classification, but I can think of regression problems from these optics as well. Okay? So this is the likelihood. So I'm not telling you anything new. This is just a way to interpret how we build our pointwise losses. We can think of it as a likelihood, as a negative likelihood function. What about the prior? It's the prior on theta, on the parameters. So what do you do in MAP, in a maximum posteriori estimation, if you don't have any prior? If you don't have any prior, assume a uniform prior. A uniform prior means that this term will become constant, right? And then the maximum posteriori estimator will become a maximum likelihood estimator because the prior is constant. So this uniform prior gives maximum likelihood, right? This is what we had in cross-entropy estimation, in cross-entropy minimization. You can assume a Gaussian prior. This is also a very popular prior. So you're assuming that your theta are distributed around 0 with some covariance, some fixed covariance, diagonal covariance with the parameter sigma squared. And the prior will become the Euclidean norm theta squared. And in different literature, it is called differently, but this is weight decay or some other type of weight regularization, right? So this is a very standard regularization of the weights in a neural network. Okay, so basically you can think of that regularization term as a Gaussian prior on your theta. Okay? So with this view, let's now move to a slightly more interesting training regime. that can be called domain adaptation. So I'm assuming that I have some training set, labeled training set, coming from what I will call a source domain. Okay? And so imagine, for example, that I'm building, let's make the situation interesting. For example, I'm building let's say some neural network that is going to predict the outcome of some medical condition, for example. Okay? The result of some treatment. Okay? But in order for this treatment, for this neural network to work, I need to train it on some data, right? So I can go to the lab, I can collect data with ground truth labels from the lab, right, and train my predictor on those data. Okay, but unfortunately, what you can collect from the lab is not necessarily what you see in the wild. What you see in the wild, well, it's called what you see in the wild the target domain. In the wild, you don't have labels. There are no labels, but you have zillions of data points potentially. So you have an unlabeled training set that might come from a different distribution. That's why I'm calling it Q and not P. Okay? So you have another training set, unlabeled training set. It's an unsupervised training set that I will be denoting by T as opposed to S that denotes the source domain. And my target is to estimate Q yx. I don't know why this bug. Q yx from S and T. So I would like somehow to leverage both the labeled data and the unlabeled data to train my classifier in this case, or my regressor, depending on what is the label space. And the particular setting is called semi-supervised learning. In that case, the source space and the target space, or the source distribution and the target distributions are the same. So just imagine, for example, that medical example, obtaining ground truth labels might be a very costly process. Costly and painful and maybe unethical even. Let's say you need to collect biopsies for your ground truth. You wouldn't collect biopsies on healthy population, for example. So you have some access to these ground truth labels, but you have many more unlabeled samples. Okay, and you want to somehow use both of labeled samples and unlabeled samples, but they come from the same distribution. So this is called semi-supervised learning. You have partially labeled training set. So some of the training samples are labeled, and some of them, usually the vast majority, are unlabeled. Can you actually use those unlabeled samples to help you training a classifier or a regressor that is trained in the supervised regime? Can you actually use unsupervised labels, unsupervised samples to help the supervised training? Of course, if you don't have any labels, you cannot predict anything, right? So you have some amount of labels. Now, if you look again at our general formulation of supervised training as a maximum posteriori estimation, you can clearly see that unlabeled data are completely useless in this first likelihood term, right? Because it depends on y, and you don't have y. So that term can be only evaluated on the labeled training set. It can only be used for the prior, right? So the only term that remains is the prior. So I will concentrate on this prior term. And let's see whether we can use unlabeled data for the prior. Now, there is a vast evidence, it's an empirical evidence, I don't think there is any theoretical justification to this, that the information content of unlabeled data, basically the usability of unlabeled data, decreases as the different classes, I'm specifically talking about classification problems, that as the different classes overlap. So if you have well-separated classes, you can actually make more use of unlabeled data. So therefore, I'm going to demand that we have well-separated classes. Okay, so if they are not well-separated, I'm not going to make use of unlabeled data. Yes?
What do you mean by well-separated?
Okay, so let's define rigorously what I mean by well-separated classes. Okay, so well-separated classes, in my language, is the fact that the label y given the instance x has low uncertainty. Okay? So basically, the classes are tight. I give you the instance, and you know quite a lot about the label.
You mean human supervisor or classifier model or?
Data contained in the actual ground truth distribution. Okay. So basically, this measures in some way the size of the cluster, the size of the cloud of points in the label space around.
So like if you assume that, for example, the data is coming from multiple Gaussian distribution, then each Gaussian is well separated from the other.
So if the data come from a Gaussian mixture model, this will control the variance of the Gaussians. Exactly. So well-separated classes, again, we said that Y given X has low uncertainty. An information theoretic way of quantifying this uncertainty is called conditional entropy. Okay, so the conditional entropy is the amount of information. It actually can be measured in bits or nuts, depending on the basis of the logarithm that we're going to take. It's the amount of information needed to describe Y given X. So I give you X. How much additional information do you need to encode to describe Y fully? Okay? And this is given by the conditional entropy. Conditional entropy is simply the expectation of the negative log of this likelihood function, p theta of Y given X, with respect to p theta Y given X. Okay? You can give it different names, right? You can think of it as information gain. But basically, this is the conditional entropy. And let's write it explicitly. We have sum over all labels Y. So I'm thinking of the labels as a discrete space. I have sum over all labels Y. This basically, I'm writing this expectation explicitly of the integral of negative. So it's negative log. So it's negative p y given x log p y given x with respect to dqx. dqx is the distribution of the data in the target domain. In the semi-supervised setting, q and p are the same. Okay? And of course, this is what produces this p theta is my neural network, right? That's why it depends on the parameters theta. So my neural network models the likelihood function. Okay? So it's a very complicated parametric model of the likelihood function. Okay, so I can write, of course, I can write this integral as, I can approximate it by a sum over the unlabeled training set. And of course, I can use both labeled and unlabeled samples for this purpose, right? The main point is that I don't need the labels to estimate this integral. Okay, so I'm estimating it as a sum. Okay, and this is just the size of the target training set. Okay, so this is my conditional entropy. What is cool about conditional entropy that is, for example, it is completely invariant to the reparameterization of my model. So I can write it in any form. It will be this quantity will remain the same, no matter how I parameterize my p. And by asserting class separability, I mean that the expectation of this conditional entropy over theta, with respect, obviously, to some distribution, to some prior distribution of theta, has to be small, smaller than a certain quantity epsilon that I'm going to put by hand. And then it will just pop up as a regularization parameter. Okay, so this is in my language is an expression to the class separability. Okay, so I have the expectation of the conditional entropy smaller than a certain threshold. Question? So my assumption is that this model is rich enough. Yes. So if the model is not rich enough, so you will see that we will be able to think of the loss as comprising two terms. One term can be interpreted as a regularization term. So you can take a very complicated class of models, and then the unsupervised part will be a regularizer. Okay, so basically, you will not suffer from excessive expressiveness of the model. So it would make sense to take a very rich models class here.
Don't don't take a rich model that you can't write what you're writing.
Well, I'm trying to impose this, but so let's assume that this can hold, and we'll see where it leads. Right? Epsilon. I'm not saying which epsilon I'm selecting. Right. So for an epsilon big enough, this will hold. Okay. And of course, this expectation is the integral of the conditional entropy parameterized by theta. I'm thinking of theta as a parameter here. Integral with this density p theta, which is our prior on theta, right? Again, remember our use of unlabeled samples is only good for the prior. It's only good for this quantity. So this is the quantity I would like to find. Okay? And now I will make no additional assumption on theta. So when I say no additional assumption on theta, what does it mean in terms of prior? So if I say I make no assumption on theta, what prior does it translate to? Uniform prior, right? Uniform prior. So here I want this to hold, plus I'm assuming a uniform prior on theta. So uniform prior means that, again, as uniform as possible. It cannot be uniform, because uniform prior typically will not satisfy this inequality. Right? So uniform, what is particular? So if I give you an information theoretic measure of uniformity of a prior, how can you express it? Uniform means, in terms of entropy, uniform means maximum entropy, right? Doesn't depend on the scale, by the way. So uniform means maximum entropy. This is the biggest amount of disorder you might have. So essentially, I would like to maximize the entropy of theta subject to that condition on the conditional entropy of theta. Basically, this is the condition on class separability, right? So I want the classes to be separable enough, and subject to this constraint, I would like to make my theta as uniform as possible, as maximum entropy as possible. And this is typically known as the maximum entropy principle. So let's write it explicitly. My optimization variable is this function p theta. This is the density of theta, my prior probability density of theta. This is the conditional, this is the entropy of theta, not conditional. This is the entropy of theta, subject to this constraint, right? I'm writing it explicitly. Do we have another constraint? So by the way, I wrote it with epsilon, with equal to epsilon, not smaller than, because typically this is what I'm going to achieve, right? It will be an active constraint. What else is missing? Can p be any function? So p has to be a distribution. It has to be non-negative and subject to this normalization constraint. Okay? So when you see a constraint problem, how do you approach it? There is a famous French person who is associated with constraint problems. So you introduce Lagrange multipliers, right? So you have these two Lagrange multipliers, lambda and mu, associated with each of these constraints, right? Both are equality constraints. It's easier to work with equality constraints. And what we have here is a variational problem, right? So we are minimizing a functional with respect to a function p, right? So I can write what is called the Euler-Lagrange equations, and they will give me the p that minimizes this function or maximizes this function in this case. But I can actually do it pointwise. So let's fix theta. So once I fix theta, the value of my density at point theta becomes a scalar variable, okay? And now I have a pointwise optimization problem. It's not a variational problem anymore. The optimization is scalar. So let's call h the conditional entropy of y given x. When I fix theta, this is also a constant, right? So this is a constant and p is a variable. So I have this maximization of this expression, right? P log p plus lambda hp minus epsilon plus mu p minus 1. Okay, this is just the translation of what we had before here, right? So instead of integrals, I'm sampling at fixed theta. Okay, I take the derivative with respect to p, equate it to 0. Okay, just skip the details, I'm getting p equal to some constant times e to the power minus lambda h. Okay? This is the solution of this. This is the solution of this problem. Okay? So essentially the arg maximum of this problem, of this constraint problem, is a function of the form c minus e to the power minus lambda, and h is h theta, y given x. Okay? So let's take the negative log of this minimizer, because this is what we care about. So this minus log p theta equals lambda h theta y given x plus some constant. Okay, so and this is the actual expression that I can write. Okay? So this is my prior on theta. Remember that we always wrote conditioning on x in the prior. And we actually have conditioning on x because we have the actual x's that are coming from the training set, from the unlabeled training set. Okay, so we have a prior on theta. We had the likelihood term that requires labels. So we can write our loss function, right? We have a combination of two terms. One comes from the labeled set S, and the other one comes from the unlabeled set T. Okay, and again, T can be generated from a different distribution, like in domain adaptation problems, or T can be generated from the same distribution, like in semi-supervised problems. Okay, so basically both. So this loss function accounts for both settings. So it will just depend on whether I have the data distribution of the x's here and then the x's here the same or not. Another point that is very important, when we are doing domain adaptation, this probability function cannot be the same, right? Because the data are distributed differently in the source domain and in the target domain. So I do want to find the same vector theta, but I want somehow these probability density functions, these likelihood functions, to be different. Okay, so you will see in the tutorial one particular method for doing domain adaptation that uses something that looks like batch normalization in order to achieve two different. So basically, one set of parameters implementing two different likelihood functions. One for the source set, another one for the target set. Okay. Of course, in the semi-supervised setting, we don't need to make this distinction. It will be exactly the same likelihood function that we'll use in both cases. Okay. Any questions? So maybe one important distinction. So there is another, I would say, closely related task that often arises in real problems. That is called transfer learning. So in transfer learning is a slightly different setting. In transfer learning, we would like to use, let's say, some labeled or maybe unlabeled or maybe semi-supervised set on which we train to perform a certain task, let's say classification of something, in order to solve a new task. So we would like to leverage our ability to solve task A in order to solve a different task B, for which we might have some small amount of data, some scarce training set. So that is called the transfer learning. Basically, we would like to use data for a different task to solve a new task. So you see, it's slightly different setting compared to what we discussed here, where we want to adapt or use labels on some differently distributed data set and unlabeled data on the target set, basically to solve some classification problem, for example. Okay, and another related problem that also arises frequently in learning is called one-shot or few-shot learning. So imagine that you learn how to distinguish between different animals. Let's say you have 100 different animals, and now I'm showing you a unicorn. So you've never seen a unicorn, I'm showing you one example of unicorn. Now go and add another class to your classifier. Just from one example. So you have a zillion of different animals, but you have never encountered a unicorn. So you have one example, and you need to update your classifier to be able to correctly classify all the unicorns that of which you have observed just one instance or just a few instances. And children do it very, very efficiently, just from one example, right? So we have an incredible ability to do one-shot learning. And it's a very active and unsolved research problem, at least as of today, how to do it using machines. Right? So it's an important problem. But again, it is loosely related to semi-supervised and domain adaptation problems. Okay, any questions? So if there are no questions, what I plan for next week is to start talking about reinforcement learning. Maybe we'll need a little bit more time in the following week. And then I will give the floor to Avi to talk a little bit about hardware. And then we'll basically talk a little bit about non-Euclidean, learning on non-Euclidean domains, on graphs and manifolds. Okay? Thanks.